Okay, so it's 5 p.m. We'll start. Okay, so welcome to week 11 of Next Generation Sequencing Technologies, Data Analysis and Applications. So last week we did some hands-on with R, programming and different packages for R. We used DSIC2 and other sorts of packages. So we are coming towards the end of the course. So this week we'll learn a little bit about genome assembly and how are the different algorithms for the genome assembly and how can you basically do genome assembly. And mostly we'll focusing on three methods that is covered. So basically shortest common substring, overlay or overlap graph, and De Bruijn graphs. So we'll go through them one by one. And as usual, like during the end of this uh, session, we'll have some question answers to be discussed from prior assignments. Okay. Okay. I'll just quickly check if anybody is doing. Okay. Yeah, I'm in the correct link. Okay. So before we come to what is how do we do genome assembly and everything, firstly, like why do we need to do genome assembly and like, why are we looking for different methods for doing genome assembly? So as we know, okay, from different genomics pipelines that we've learned earlier. So one step in the pipeline is basically you get the reads, you see the reads, quality control using different kind of things, and then ultimately you align the reads with the particular reference genome. So after alignment, you can see the gaps in the genome, the kinds of mutations that has particularly occurred in your sample compared to the reference one, and what are the variations and everything. You can check that. Now, building the reference genome requires building it from scratch. You don't have any other genome to fall back against, so you need to design your reference genome from scratch. Now, how do we do that? That is the concept of genome assembly. So basically, you have very short reads, as in from sequences like Illumina or Nanopore. Nanopore is slightly bigger, but technically, in context of the whole human genome, you have very short reads. Now you need to assemble these reads one after another and get the whole genome. Now, this might have been easier if we knew the location of the reads, from where these reads are originating in the genome, but that we don't know. So we have randomly a set of reads, and we need to combine them to make the whole genome. Now, if there if the reads were very distinct, say for example, one read is from 1 to 10, next read is from 11 to 20, so 21 to 30, 31 to 40, like that. If they were very distinct like that, with no overlaps, it would have been much easier. We would just concatenate the reads and try to get the whole genome. But here, the cases are different. So basically, when you try to sequence the genome, you amplify the genome, right? You use PCR and other techniques to amplify the genome, and then you break it down into shorter fragments. Now, these shorter fragments have overlap between them. So the you cannot directly concatenate two reads, two or multiple reads to get the whole genome. There is a certain amount of overlap, and you need to identify that overlap with every particular read. Now, here the concept of coverage comes because coverage is what decides how much overlap between two reads might be. So, what is coverage? It is referred to the number of reads covering a particular position in the genome. So, for example, this particular position in the genome is supported by this T basically is supported by 1, 2, 3, 4, 5, 6 reads. So, coverage at this particular position is 6. Now, if you have a higher coverage, what means is you'll have more overlapping reads here that supports a particular base. So Technically, while doing sequencing, having higher coverages are better so that you have the most amount of information, you do not lose out on anything, and you have multiple evidences for the base caller to call it as a particular base. So coverage is quite important in that aspect. So what is this is part is coverage. Now, what is genome assembly and what is the principle for genome assembly? The more similarity there is between the end of one read and the beginning of another, the more likely they are to have originated from the overlapping stretches in the genome. So, for example, let's take these two particular reads. Sorry, these two particular reads. So there is a lot of overlap between these two particular reads. See, uh, except for this middle A, almost and the last two bases here and the last four bases here, almost there is an entire overlap. So if you see the original genome from where the reads originated, you'll see they are originated from the same part of the genome. So this part is common, and this is unique to the second read. This is unique to the first read. So the principle, the basic idea behind this is the more similarity there is between the end of one read and the beginning of another, the more likely that they have originated from the overlapping stretches of the genome. This is the principle we'll be going by. Now, let's say two reads truly originated from. Just give me a second, guys. I'll back in a minute. then it is called a directed graph. Uh, Sorry, disconnected. Okay. Okay. So you have a set of vertices, which are your nodes, and you have a set of edges which connect two nodes together. If there is a directionality associated with the edge, then we call it as a directed graph. If not, we call it as an undirected graph. So it contains, as defined, it contains V vertices and E edges, and it is represented by this notion G in bracket V comma E. And directed edge is a ordered pair of vertices. So basically, there is an odd directionality between the two vertices. So, for example, A to B, you can move from A to B, but you cannot move from B to A. So because there's a directionality associated with the edge. Now, first is the source from which you are moving away. So from A, say for example, you are moving in two directions. This is the source, and this is the sink. So ultimately, if you are moving from here, it is the sink. So from A to B, you are moving here. C to B also you are moving here. So this is the sink. So from if it is a directed graph, you'll have directed edges between them. Now the node of origin for that particular edge is the source, and where it ends, it's the sink. Now the vertex is drawn as a circle, edge is drawn as a line with an arrow connecting two circles like this, and a vertex is also called a node or a point, and edge is also called the arc or a line, and this directed graph is also called a digraph. Right, and this is represented in this way. So G of V comma E, so V vertices, it is represented like a set of four vertices or four nodes, and E are your edges connecting AB, then AC, then CB, like that. Okay. Now, oh, sorry. I just got disconnected. Can you see now? Yeah. Okay. Okay. So let's go back a little bit and cover this again. Yeah. So when you're trying to find overlaps between two particular reads, the way to do is to build a directed graph where your directed edges connect your overlapping nodes. So basically, these are your individual reads, and each of them is represented by a node. Now, these nodes will be connected like this. So you have two nodes, and it will be connected by an edge. Each of the edge will represent the amount of overlap between these two particular reads. So the overlapping sequence between these two reads will be shown by the edges. And as I was saying, key directed graph, uh, you have a sense of directionality in edges. You have to move from one point to another, so you have to follow the direction. And this is how it is represented. G of V comma E. V is the set of nodes, like I said, the four nodes that we have here. And E is basically the edges, how the edges are constructed. That information is given by the E set. Okay. Now, if you want to find overlaps between reads and you want to build an overlap graph, so the overlap will is basically a prefix or a suffix match of at least, for example, in this case, it's three characters. It can be more or less depending on what you're trying to do. A vertex is a read, and a detected edge is an overlap between the suffix of the source and the prefix of the sink. So basically, source is from where the arrows are originating, where your uh, edges are originating, or edge is originating, and sink is the node at which your edge is like getting deposited, like it is ending there. So uh, you have a set of reads, and basically you want to find the overlap graph. So basically, what you are see the condition is at least three characters should overlap between the source node and the sink node, right? And the vertex is basically given as the different reads. So these boxes are your vertices, and the directed edge is an overlap between the suffix of the source and the prefix of the sink. So this is your source, and the suffix of the source is here GCC, last three reads, and the prefix of your sink is a GCC as well here, right? So this is overlapping between them. So there is a three character overlap, right? Now, this is how an overlap graph looks like. So you have different reads, you calculate overlaps between these particular reads, and you build a graph like that. That is what an overlap graph is. Now, this overlap graph could contain cycles as well. A cycle is a path beginning and ending at the same vertices. So, for example, this starts from here, then goes here, then this again comes back here. Now, this can happen in a few particular cases. Firstly, is when the DNA string is itself circular. So there is a circular element to the string. So for example, bacteria plasmids that we have, it's a circular genome. So it's basically it is supposed to be connected like that. So these kind of uh, uh, cycles you can find in circular DNA, for example, bacterial genomes. But these cycles can also be present in normal DNA as well because due to repetitive portions of the DNA. So if there are repeats, say for example, this part is a highly repeated. These two nodes are basically highly repeated ones. So there is high amount of chance that this node will overlap a lot with this node because it's a repeat. It's the same thing that is going on and on again. So that is why genome assembly becomes trickier in the parts of the genome where the reads are very repetitive in nature. The DNA is very repetitive, and the sequence is very repetitive in nature. So one such example is basically you can consider the Y chromosome of the non-par regions of the Y chromosome. There are a lot of repeats. So that is why what happened is like the whole chromosome of the whole sequence of the whole Y chromosome was not completely known until like a year or a year and a half back. Before that, we only knew the part of the Y chromosome that has less repeats and it's easier to resolve. So because for creating reference genomes, you need to like build the genome from scratch, and the only way to do it is basically using genome assembly. So while you are trying to do that, if you have a lot of repeats in your reads, it's very hard to resolve that portion of the genome. So that has been an area of research until we got the whole Y chromosome there. But it's still a very on topic of ongoing research, right? Okay. Now, while while you are trying to find overlaps, so how will you find the overlap? So, for example, you have a length L suffix of X and which matches a length L prefix of Y, where L is the given amount of overlap that you want. So here in this case, we take L equal to 3. What you want to do is basically look in Y. So Y is your sink and X is your source. So from the suffix of X matches with the prefix of Y. Now you want to do is look in the Y chromosome, look in the Y read for occurrences of length L suffix of X. So for example, this is your suffix of X, and these are your two reads X and Y. So this is the suffix of X, which is GCC. You are trying to look for this in Y, going from right to left. So you start from here, and then you traverse on this end. Sorry, you start from here and then you traverse on this end. You do not start from the end. So basically, for the source, you check the suffix, and for the sink you check the prefix, this part. So GCC, where it is overlapping, if you move in from here, the overlap is in this part of the uh, genome, right? So GCC, the last part, overlaps in the middle of Y. Now if you extend this to the left, we confirm that a length 6 prefix of Y matches with the suffix of X. So this is the suffix of X. It starts with TAGGCC. Now, you wanted to find where other region in the read is GCC present. So in this case, GCC is present in the middle. But if you move to the left, you see there are more matches. Since your condition was only 3 matches, you wouldn't have found this whole 6 read wala match. But if you do that, you will find there's this whole six sequence overlap between these two particular reads. Right. Now, you want to build the overlap graph. Like, how do you do that? So you you make it into the small pieces of reads, and then you see how many are overlapping. Say, for example, let's like, take these two nodes. So GCA TT80, and this is ATT8080. Now see the last five reads here, ATT80 and ATT80 are overlapping here. So you connect these two nodes, and on the edge you put a 5. For example, this and this. In this two, the last three, TAT and TAT matches here. So you connect this node and put a 3. So each of the edge label, each of the edge label is giving you the overlap strength. And this is the original string for that, right? The whole graph that has been made, it is made out of this particular original string. Now, if you can imagine, if this small string can get us such a complicated overlap graph, so you can imagine how complicated it will look if you take the whole genome. So it's going to be very computationally intensive for like working on it, and also like storing it is also a very big issue. So we need advanced computation power to resolve reads like this. Now, one strategy to find this particular overlap is the shortest common substring. Now, if you have a set of reads and you are trying to find, let me define the problem statement properly. So you have a set of reads. Now you are trying to find the shortest substring, or the shortest common substring that is there that covers all these reads. Say, for example, you have these set of reads. So 1, 2, 3, 4, 5, 6, 7, 8. You have 8 reads here. And if there are no overlap, as I was saying, you can just concatenate them, and you just concatenate them, and you found a 24 length sequence of length 24. So there are 8 reads with um, each of read length of 3. So you get a 24 base the length of if you concatenate. Now, if you try to find the shortest common substring, you do not want to just concatenate. You have overlaps. You want to see the shortest substring, common substring that is possible that covers all these particular strings. So that is where you try to see overlaps. These three A's are overlapping with these two A's here, like that. If you build the overlap thing, you get the shortest common substring as a tenth, a 10 length uh, base pair, a 10 base pair length sequence. Now you see this is kind of like 2.5 times lesser than if you just concatenate the reads. Now, this is the shortest common substring, but it is uh, it is harder to do if there are if you're working with real life genomics data. So it's the amount of overlap that you have to find is very hard, and then after you have found the overlap, you need to set them up and get the whole string. Now, this is a very telling problem in terms of genome assembly because of the amount of time and space this algorithm will take. We'll see that in the further slides. Now let's imagine a modified overlap graph where each edge has a cost which is negative to the length of the overlap. So if you travel that particular edge, so for if you are traveling from this edge to this, your uh, the cost of traveling that, if you're doing some sort of optimization, the cost of traveling that will be negative of the length of overlap. Shortest common substring corresponds to a path that visits every node once, minimizing the total cost along the path. So that is what you are trying to do. You are trying to run the algorithm where you'll uh, you're trying to find the path that visits every node at least once, and also it needs to like minimize the cost of those visits. So you'll have multiple of these models, and which of the models is giving you the lowest cost error is your uh, uh, shortest common substring. Now, if you try to do this in real life, what you find equivalent to is the traveling salesman problem. So the traveling salesman problem is, I'll just quickly show you here. Yeah. So this is a traveling salesman problem. So these are nodes are known as are like depicted as different cities. So for example, a salesman starts from city one. Here is the start. But the condition is he must travel all the cities once before returning home. So it has to travel 12, 3, 7, 5, 6, 4. Every node it has to travel, and then it has to return to its own home. The distance between each city is given and assumed to be in the same direction. Only the links shown are to be used, and basically the edges, those are the edges that are there, those only you can use. You cannot, say, for example, jump from 1 to 4 directly. You have to go through 3 like that. So all the edges you have to use. And your objective is to minimize the total distance traveled. Now, this is a NP hard problem. There are like no good solutions for this. So technically, we cannot go on with this particular algorithm. Now, if we do one thing, if we disregard the weights and just look for the path that visits the nodes exactly once, that is the Hamiltonian path problem, which is the NP complete. So you can say key the shortest common substring problem is NP hard. So I'm not going into the detail of what is NP hard and NP complete. You can just take a look in the traveling salesman problem, you'll understand what it means. It's basically meaning like it's very hard to do. If in like very nominal words, it's basically you cannot, it's not physically possible. Right. So yeah, you can take a look into the Wikipedia page. This is a very actually this has a good history of like how it came about and everything, the Hamiltonian cycle and everything. Right. Let's move on. So our problem of finding the shortest common substring among a set of strings is NP-hard. So if it scales up, you won't have enough computational power or efficiency to do solve this particular problem. Right. Now let's try to find the shortest common possible superstring, and we are trying to find basically these are your shortest common substrings, and when you concatenate them, you find the superstring. Basically, all the reads are part of that particular superstring, right? Now, if you try to find the shortest common possible superstring, this is a greedy algorithm to do that. So non-optimal superstrings can be found with a greedy algorithm. At each step, the greedy algorithm greedily chooses the longest remaining overlap and merges with its source and sink. So basically, you have a set of reads, you pick a read and take whatever is the so basically you try to look for reads. There are a couple of reads which both of them have the highest overlap. So that is what you're trying to iterate and find every time. Now, this is the greedy algorithm, and if you find that, you just merge them, and in the next step, you merge the previously merged sequence with the most overlapped read that you have already present in your data. Now, this greedy algorithm is not guaranteed to choose overlaps, yielding the shortest common substring, but greedy algorithm is a good approximation. The superstring yielded by the greedy algorithm won't be more than 2.5 times longer than the true superstring that you're trying to find. Now, this is an example for that. So, if you take just one overlap here, L equal to 1, yeah, these are your set of reads 1, 2, 3, 4, 5, 6, 7, 8. So, in red, so you're starting out with 8 strings. Now, in at each step, you are trying to find a couple of reads which are having the maximum amount of overlap. In this case, the overlap is 1. So, in red are the strings that get merged before the next round. So, in the next round, these two are merged into one. So AAB and BAA. uh, yeah, so AA is common, right? So it makes it into ABB, right? So you remove the A and just merge them together. Same in the next step, ABB and BAB. B is common here. So basically it moves into AB, AB like that. So this is this one. Again, this is has the most common with this BBA. So you move from one step to another, checking which of the two strings are having the most overlap. Now, ultimately, what you find is this particular string. which is the superstring that you have found using the greedy algorithm. But if you look at the actual common substring or the common superstring, this is actually the common superstring. The sequences are quite a bit different, but in terms of length, it's not that far off. Say this is like 3, 6, 9, 11, and your original has 3, 6, 8, and 10. So there's only one base. In terms of length, it is one base pair off. But in terms of the getting the original sequence, it's not very good, right? So uh, let's move on. Okay. Now we were building overlap graphs, and like how we were doing is basically you find the build the over sorry you build the overlap graph, you bundle stretches of the overlap graph into contigs, and you pick the most likely nucleotide sequence for each contig. Now we'll do this in great detail, but yeah, this is the idea. Suffix of one read matches the prefix of another. Here it is, and in this case it was 6. Right. Now you can do the same thing, try to find overlaps using suffix trees as well. So in the first or second class, I don't remember, we talked about different algorithms for alignment. So there one was the suffix tree where you could use break a sequence into its different suffixes and make a tree out of it. And these are your leaves, and you can travel from the node to the leaf, and you get the whole sequence. So that was the idea of the suffix tree. So say for example, you want to find the overlap between these two sequences using a suffix tree. So you put a delimiter in between and at the end, both of that, and you make the suffix tree for that. So for example, uh, so this is GSC, then this is ATA, this is one suffix tree, one branch that leads out to your first path. So basically this is your query. So move from the node to the leaves. So this is GSC, then from here you see there's an ATA, so this is one path. Next is basically ATA GSC. It's basically the opposite, right? So if your GACATA is your query, then from the root you follow the path labeled with the query. The green edge tells you that length 3 suffix of the second string equals to the length 3 prefix of the query. So basically you just need to travel from here, then you'll get the original suffix, original query, right? Now, the idea is to build a tree, this suffix trees, and for each string, work down from root and report any outgoing edge labeled with a separator. Each corresponds to a prefix or suffix involving prefix of a query string and suffix of a string ending in the separator. Now, we'll go into the details here. Say, for example, this is your query, ATAGSE. This is your root. Here is an A, there is a TA, then there is a GSC. Now, the thing is, there can be, say for example, in this node, when you come, there can be other nodes that you can move to as well. The thing is, in this one, say for example, the green ones are telling you that if there is a green here, what it means is there's a dollar sign here. So that means this is the end of the first query. Right? So in from this position, you can't move to this dollar sign. So you move to the other paths here, and this is also a dollar sign, but it does not give you the whole sequence. Now from here also you can move to this or this, right? You won't move to here because it's a dollar sign. So wherever there is a dollar sign, that means around it you can find the whole sequence. So for example, here is the dollar one. So this whole sequence is through the other path, right? So you can't move to the dollar sign. You can move to the other paths in the dollar, other than the dollar. And this is how the overlap looks like. So this is generalized suffix tree where you try to move from you make the whole tree based on the suffixes, and then you move from the root to the leaf, trying to find the best possible string. Now, this is a very time com com uh, time consuming and also computationally intensive as well. So if you have n strings of length d and total length is given as capital N, which is product of the length of the strings and the number of strings. And A is the number of string pairs that overlap. So for building the suffix tree, it is going to take you linear time. To walk down the rate paths, it's going to take you linear time. And to report out all the overlaps, it's also going to take you linear time. Overall, it takes a linear time. So bounds don't include n square, but A is also, I mean, this is not the worst case scenario. The worst case scenario is quadratic time, but in generally, you do not go there. It's most probably in linear time only. Now, this is one way to find overlaps is using suffix trees. You can also do it with dynamic programming. So remember dynamic programming when we are doing multiple sequence alignment and like this protein matrices and those things. So there also we came up with the dynamic algorithm, dynamic programming algorithm. Here also it is there. And say there are n strings of length d, same thing, total capital N equal to small n d, and A is the total number of pairs with an overlap, and the number of overlaps to try is much greater here. It's quadratic in nature. Size of each dynamic programming matrix will be quadratic in nature, and overall it will be quadratic with respect to both your number of pairs and your amount of overlap. So if you compare this with the suffix tree, the suffix tree is doing much better in terms of complexity, which is linear in time. And A is the worst case scenario is n square, which is still better than n square d square, right? It is n square d square, but here the worst case scenario is n square. So the worst case scenario for suffix tree is better than the dynamic programming matrix, right? But dynamic programming gives you more flexibility and it allows for mismatches and gaps, which is very crucial because your genome will contain those mismatches and gaps and there will be no complete overlap. In practice, overlappers are between the two using indexes to filter away non-overlapping pairs and then dynamic programming for the remainder of the algorithm. Now we come to the basically the last portion of that is De Bruijn graph assembly. So for De Bruijn graph assembly, it's basically it's actually the concepts behind every algorithm for genome assembly. It's quite similar. You find overlaps and then you try to connect the two strings. How you're doing that is different for different methods. So this is another method that kind of uh, agrees with the basic principle, but this is a little bit more sophisticated method to do that. Now, you have, you know what a k-mer is. It's a substring of length k. So this is your string, and all the three mers of this S will be three length substrings of a whole superstring, right? So this is your whole superstring. All three mers of X will be GGC, GCG, like three overlaps. Like here it's three, then again three, like that. So these are all your three mers for S. So the K mers is basically the substring for that particular read, right? There's a read and you want to take a particular substring out of that read. That's the K mer. And we'll use K minus 1 mer to represent a substring of length K minus 1, which is very evident. Now, you say, for example, you have these particular reads, sorry, particular K mers here. So here k equal to 3, so these are 3 mers. So if you break down this particular k mers into more small substrings, so if this is the read AAB, the left two elements AA is the left k minus 1 mer, so we are referring to this. So AA is k minus 1 mer and AB is the right k minus 1 mer. So there's a left mer, there's a right mer. So it's k minus 1 for left, k minus 1 for right. So if this is a 3 mer, this is its left mer, which is AA, the first two, and this is its right mer, which is AB, which is uh, last two. So this is A is called as AAB's left two mer, and AB is called as AAB's right tumor. So yeah, it's quite evident from that. Now, if we take each length 3 input string and split it into two overlapping substring of length k, And we call this the left tumors and the right tumors. So for example, you take all the three mers and you break it down into left mers and right mers of k minus 1 length. Right. Now you let these two mers be nodes in a new graph. Right. So these are your two mers like here. So there are repeats. So you only take the like non-repeated ones. So AA, AB, BB, and BA. So these are your four without repeats reads. So AB, AA, BB, and BA. Now you take these nodes into a new graph and you draw a directed edge from each left tumor to the corresponding right tumor. So, and where there are repeats, you put a self edge. So AA, there's a repeat, you put a self edge. Other than that, you connect. So AA connects with AB. So this is AB. From here it goes here. AAB connects to BB. So AABB like that. So here are the overlaps given. So each edge in this graph corresponds to a length of 3 input string, which is the same here, and all the strings that are involved here are given. So if you overlap between AA and AA, the string that you get is AAA. Now, if you overlap between AA and AB, what you get is AAB, right? Like that. So AA and AB, it's AAB. AA and AA, it's AAA. AB and BB, it's ABB. So all the overlapping things are taken into account, and each of the graph will correspond to a length of 3 input string. Remember, we started with a k-mer of 3, but we broke it down into tumors. Now we are trying to find overlaps between these particular tumors. Now, before we see how we can get the genome back, one concept we need to understand before we do that. So, in graph theory, there is a concept of random walk. So it's a random process which describes a path that consists of a succession of random steps on some mathematical space. So for a graph, you have a starting point. You select a neighbor at random. So for example, you're starting here. You select a neighbor at random. There's only one neighbor to go here from because you cannot go back here because it's a directed graph. There's one neighbor to go here and you move there. From here, you check what are the possibilities where you can move, and with a certain amount of probability, you'll move into the corresponding edge, right? So you move to a selected neighbor and repeat this process until a termination condition is verified. The random sequence of points selected in this way is called the random walk of the graph. So there are various types of this random walk. One is basically random walk with restart, which is basically you terminate the condition and then you restart a walk again randomly to see what are the possible random walks in the graph. Now, uh, this is a this is a technique that is used to study a network vicinity of gene, protein, seeds to study their function. This method is based on the idea that nodes related to similar functions tend to be closer together in the networks, right? So if you see an example, say for example, you want to do a random walk here. So you have a graph here with vertices V and edge E. If G is a connected non-bipartite, I'll ask you to ignore this terms, non-bipartite and bidirectional. So non-bipartite, remove it. Bidirectional is basically you have no direction in the edges. You can move both ways. So this is not a directed graph. So yeah, it's a bidirectional graph. Random walk converges to a unique stationary distribution with any starting point. So however randomly you try to move, the distribution will it'll ultimately, if you do it multiple times and you try to converge it, it'll converge into a distribution which is like unique stationary distribution for every starting point. More specifically, when we perform random walk on G from the node V, we first move to the neighboring nodes with a probability 1 by degree of V. Degree of V is basically the number of edges connected to that particular node. Say, for example, you want to move from uh, this location to this location. There are only this is not only one way to do it. You can move directly from 3 to 4. You can move 3, 5, 4. You can move 3, 2, 4. You can move 3, 1, 2, 4. So there are many ways to do it. So based on the number of edges that are coming out or going in for the particular node, uh, the probability is decided. So let's take this example. The probability to walk uh, to each node in each iteration is listed in this particular uh, um, table. Yeah. So how do we get this particular amount of probability? So you start with node 1. This is your node 1. In iteration 1, so for these are your iterations 1, 2, 3, 4 till 30. So in iteration 1, you move to node 2 and 3, right? So from 1, if you move to node 2 and 3, you're moving to two nodes, and there are like you can from 1 you can either move to 2 or you can either move to 3. There are two options, and each of them is equally feasible. So there is a 0.5 probability for node 2 and 3. Now for the next iteration, in iteration 2, you move from node 2 and node 3 to their neighboring nodes. So from node 2 you can move to node 4 and 3, and from 3 you can move to node 2, 4 and 5, right? So for node 2 it's 1, 4 and 3, right? So for node 2 we can move to node 1 and node 2 each with a probability of 0.5 into 1 by degree of node, which is basically 0.5. It's basically 2 degrees. So for this for if you're moving to node 1 and 4, so the degree of the nodes, so for 4 the degree is, no, sorry. Yeah. So there are two possibilities here, right? So from 2 you can move to 4 or 1 directly, and 3 as well. So if you're trying to move to 4 and node 1 and node 4, the probability here, it's here the probability was 0.5. Now if you want to move back here, it's another multiplied by 0.5, and if you want to move back here, it's another multiplied by 0.5. So from node 2 you have a probability of 0.25 to move to either of 1 and 4. From node 3, if you can move to node 1, 4, and 5, each with a probability similarly. Like you can multiply and get the probability, and like this is how the probabilities are generated from moving from one node to another. Now, according to these probabilities, you can do a walk on the graph. So, for example, if you move to node from node 1, there's an equal probability you go to node 2 and node 3. So, first, if for example, you node to node 2, then what is the next step? You can go to node 1, which is a bigger probability than node 5. So, most probably you'll take node 1 or node 4, like that. So, you can do that particular walk using the different probabilities, and you can conclude which is giving you the better idea of the whole graph, or better traversal of the whole graph for different points. So that is what a random walk is, right? Why are we looking at random walks? It's basically because we are concerned with the Eulerian walk. So you see, we are making assemblies like these. Now what will happen is you keep adding on these two mers, three mers, whatever you're trying to add on, and then ultimately you have to get back the whole sequence, right? So for getting back the whole sequence, you need to traverse this whole overlap graph or whatever graph you're making to get the whole sequence, because you have to move from here to here, next to next to next, adding up the suffixes and seeing what the whole sequence has become. So for this case, you need what we known as Eulerian walk. So Eulerian walk is also a type of random walk. uh, and there are some conditions for Eulerian walk to work, right? So the node is when do we call a node as balanced? It's basically when the in degree and the out degree are same. So basically the number of edges coming inside the node and the number of edges leaving the node are the same. Node is semi-balanced if in degree differs from the out degree by 1. So more coming in and one less going out. Graph is connected if each node can be reached but by some other node. And Eulerian walk, the condition of the Eulerian walk is it visits each edge exactly once, not each node, just to be clear. Each edge exactly once. Not all graphs have Eulerian walks. Graphs that are called as Eulerian. A directed connected graph is Eulerian if and only if it has at most two semi-balanced nodes and all the other nodes are balanced. Right? So there are conditions for Eulerian walk. You cannot sorry. If this condition is followed, then only Eulerian walk will be possible. Otherwise, it's not. No. So for example, let's see this. If is this Eulerian? Yes, because yeah, what is the first condition? The first condition is it visits each edge exactly once. So if you just move it from here to here, it will visit each edge exactly one. And argument two is basically you need to have at most two semi-balanced nodes, which meaning the in degree and the out degree differs by one, right? So for example, so this the in degree here is 1 and the out degree here is 2. Why it is 2? One is going from this to this, another is going on itself. So 2 in degree, sorry, 1 in degree and 2 out degrees, right? So this edge you have to count twice because this is a self edge, right? So one for coming in, one's for going out, right? So this is the only in degree here. These two are out degrees. So these are semi-balanced, and AA and BB, these two are, sorry, AA and BA. So there's only one going in and no coming out. So these two are semi-balanced nodes, and these two are balanced. So there are two coming in, sorry, one coming in, one going out for AB. For BB, one coming in and one going out, right? And there's a self edge. So these are balanced, and the rest two are semi-balanced. So that is why this can undergo Eulerian walk. So how do we, so all we understand now, how do we make these De Bruijn graphs? Is basically you assume perfect sequencing because yeah, you cannot uh, do that if you cannot build these kind of graphs if you assume that there are mismatches and perfect sequencing has not happened. So for simplicity, we take perfect sequencing. So we assume perfect sequencing where each length k substring is sequenced exactly once with no errors. We pick a substring of length k equal to 5. So this is the substring that has been shown here. And you divide it into two parts. So k minus 1 left, k minus 1 right as we were speaking. So this is how it looks like. So one string is a underscore long again, and the next substring is k minus 1 mer is starting from ONG, then long, then time. So these are your two uh, left mer and right k minus 1 mer. So these are nodes in De Bruijn graph, and you add the edge from left to right. Left k minus 1 mer to right k minus 1 over. So this is how the whole graph will look like. Now, if you start from here, the probability of going so you start from here, the probability of going here is the most. Now from here you can go here, then from here you can either move up or down. So this is how the Eulerian walk will decide if which path is correct. Is this the best path to go, or is just this the best path to go? So you will have Eulerian walks for different types of paths with a different type of uh, cost functions, and the best one will yield you the lowest cost for that. And for each of the sequences, you can have multiple Eulerian walks, right? If you do the whole Eulerian walk from the source, this is your source. From this it starts, and this is your sink. From the source to the sink, you have to do the whole Eulerian walk, and you will have different possibilities, and you have to check which possibility matches your conditions the most, depending on some sort of optimization technique, or you have done some other type of optimization or whatever. But you'll have multiple of these options. After doing the Eulerian walk, you need to get the best possible genome. So this is all about genome assembly that I had to say. So I think it's pretty clear. So uh, just wanted to get the idea okay, how the different algorithms work. So we started with coverage and assembly. Then we see how we find overlaps and how the overlap can be incorporated into the concept of directed graphs. Then what are overlapping graphs and how do we find overlaps for that? And one such method is basically shortest common substring using suffix trees as well. And we build overlap graphs and using suffix trees as well here. And then ultimately De Bruijn graphs where we see k minus 1 left mer and k minus 1 right mer, we connect them. And connect the whole sequence into a set of graphs and try to do an Eulerian walk to find the what is the best possible sequence. Right. So this is all from what I had to discuss. Now we'll do the questions. Right. Just give me a minute, I'll be back.